Today we're going to be learning about mesh analysis. And mesh analysis is a tool very similar to nodal analysis, except that instead of using multiple applications of Kirchhoff's current law to solve for all of the voltages in a circuit, mesh analysis uses multiple applications of Kirchhoff's voltage law to solve for all of the currents in a circuit. Okay. So we are going to learn by doing, much like we did last Friday. I'm just going to start with some sort of example problem, and then we are going to kind of talk about the rules and all of that kind of stuff as we go. We're going to start with a circuit that only contains voltage sources, figure out the basics, and then add current sources and see how that changes everything, just like we did effectively with nodal analysis on Friday. So let's say that we have the following circuit where we have an 18-volt source like so. This will be a 10-ohm resistor. This will be a 6-ohm resistor through which there is some controlling current IX across the top here. I'm going to have a dependent voltage source, positive polarity on the left, negative polarity on the right. Let's make this 4 IX. Let's put ourselves a 15-ohm resistor here. Let's put an 8-ohm resistor up here. And lastly, let's throw another voltage source over here on the right, negative polarity on top, positive polarity on bottom. And let's make this guy 5 volts. And we now have a circuit. Okay. So our first step is simply going to be to identify our meshes. So who can remember from our first class meeting what the definition of a mesh is? And if you can't remember it, look in your notes because you should have probably written it down. So a mesh is a loop that does not contain any smaller loops. So we can see by inspection that this particular circuit then contains 3 meshes. So I'm going to put a mesh here around this path, a mesh here around this path, and a mesh here around this path. Now, generally speaking, I don't usually draw my mesh currents like this, but while we're starting out, this is what I'm going to do. You might see me do it later as just a little loop like that, indicating effectively the same thing. Okay. So we have identified our 3 meshes. Our next step is to assign our mesh currents. And realistically, these will probably be lumped together as the same in a single step when you guys do it. So we're going to assign mesh currents. And so I'm just going to call this mesh current IA, this mesh current IB, and this mesh current IC. So let me explain exactly what I mean by these mesh currents, okay? So this is just kind of a shorthand notation for the path we're going to follow, and the mesh currents flow around those paths. But so like if we look at the current flowing through the 8-ohm resistor on the top right, which would be this current right here, right? It is effectively the exact same thing as mesh current IC, as is the current flowing down through the 5-volt source. Our mesh current IB is the same as the current flowing through that dependent source from left to right. Our mesh current IA is the same as the current flowing up through the 18-volt source or from left to right through the 10 ohm resistor, okay? So the mesh currents are really just representing the currents that are flowing along the perimeter of the circuit. If we were interested in, and this is actually bringing us to our next point anyway, the current flowing down through the 6 ohm resistor, which I have labeled as IX, that couldn't be expressed as a single mesh current because the 6 ohm resistor belongs to both mesh A and mesh B. So it turns out that that current IX, since it's the current through a 6 ohm resistor that is shared between two meshes, will wind up being some combination of two mesh currents, okay? So let's go ahead and formally write down step number 3 real quick. So we are going to express our controlling variables in terms of our mesh currents. And for a current like IX, where it's on the interior of the circuit and shared by multiple meshes, what we're going to do is we're simply going to figure out which mesh current flows in the same direction as IX as the mesh current goes about its clockwise path, and which mesh current flows in the opposite direction of IX as it flows around its clockwise path, okay? So which mesh current is in the same direction? Is it IA or IB? IA, right? So as IA flows around its clockwise path, it is flowing down through the 6 ohm resistor, which is in the same direction as IX. So it's going to get a positive sign. IB will be flowing up through the 6 ohm resistor as it flows around its clockwise path. So it will get a minus sign because it is opposite the direction of IX. Now, I chose to put all of my mesh currents as flowing in a clockwise direction, okay? You don't have to make that same choice. You could choose all of them flowing clockwise, all of them flowing counterclockwise, some of them flowing clockwise and some of them flowing counterclockwise. Whatever makes sense to you is perfectly acceptable. Just note that if I had defined IB as in the opposite direction, so flowing counterclockwise, then the current IX would simply be IA plus IB because those two mesh currents would add together when they flow down through that 6 ohm resistor. So the direction that we choose for our mesh currents is important and will greatly affect our equations and all of that kind of stuff. So I just want to make it obvious. For whatever reason, and I think it has something to do with the second moment of inertia, mechanical engineers sometimes like to do theirs counterclockwise because it looks like the same moment symbol or whatever. I don't know. It's not my bag of cats. Yes, Maddox. Not necessarily. So I am of the habit of just putting every mesh current as clockwise. So we'll handle voltage polarities here in literally just a moment. Okay. So there's our third step, and that 3 doesn't look enough like a 3 for me, so let me just rewrite that. Okay. So there's our third step. Our fourth step is going to be to write a KVL equation for all, actually, I was going to say for all loops, but let's be more specific here, for all meshes. So we're going to apply KVL around mesh A, then around mesh B, and then finally around mesh C in order to set up our system of equations. Okay. So when we do KVL at mesh A, what we are doing is we're simply following mesh current A around its clockwise path. And for any voltage source, if we hit the negative polarity terminal first, we'll assign that a negative sign. If we hit the positive polarity terminal first, we'll assign that a positive sign. For any resistors, we are always going to assume that our mesh current is flowing into the positive polarity terminal. This is just so that we don't have a bunch of extra negative signs all over the damn place, okay? So when we write our KVL equation at mesh A, that would look like negative 18 volts because we hit the negative polarity terminal of the 18-volt source first. Then we're going to have the voltage drop across the 10 ohm resistor. So applying Ohm's law, V is simply equal to I times R. So the current, or excuse me, the mesh current that's flowing through the 10 ohm resistor is IA. The resistor value is 10 amps. So I'm just going to write that as plus 10 ohms times mesh current IA, just Ohm's law. And then we have the voltage drop across the 6 ohm resistor. And so this is going to look like 6 ohms times IA minus IB. So whenever we have a resistor that is shared between two meshes, like the 6 ohm resistor is, as well as the 15 ohm resistor is, we're going to have a combination of mesh currents because we need to find effectively the total current flowing through that particular resistor and then use that in our Ohm's law expression. So I've circled back around to my original node. So I'm done with this particular Kirchhoff's voltage law equation. And now we're going to write a KVL equation for mesh B. And we're going to do the exact same thing, right? So anytime we see a positive polarity terminal on a voltage source, the voltage will get a plus sign. Anywhere we see a negative polarity terminal first, the voltage will get a minus sign. And for any resistor, we are just going to assume that our mesh current that we're following is flowing into the positive polarity terminal. So I want you guys to tell me what's going on, and we're going to start at the bottom left-hand corner of mesh B. So what's the first thing that we see? So the 6 ohm resistor. Okay, so what's the voltage drop across the 6 ohm resistor when we're following IB around? Putting it in terms of mesh currents. So is only IB flowing through the 6 ohm resistor? IB minus IA times 6 ohms. Okay. What's the next thing that we see? Positive or negative? Positive 4IX. What's the next thing that we see? And what's the current? IB minus IC. So 15 ohms, IB minus IC is equal to 0. Ashton, I saw you doing some hand gestures there. There's no problem with that whatsoever. I just want to make something kind of obvious. So if I choose all of my mesh currents to be in a clockwise direction like I did, when we're following mesh current IB around its clockwise path, IA will be in the opposite direction and IC will be in the opposite direction. So if we consistently choose all of the mesh currents either clockwise or counterclockwise, we know that in any element where two mesh currents are flowing, the one we're following is positive and the other one has to be negative. So that's the main reason why I consistently choose everything to be clockwise. Okay. So if you follow that as well, you don't have to think about the direction of the other current. It's always negative. I think there was a hand up in the back. Okay. So now let's do KVL at mesh C. So you guys tell me what this one is going to look like. So 15 IC minus IB, absolutely. Next. Eight ohms times IC. And lastly, minus 5 volts is equal to 0. And now notice that we have 1, 2, 3, 4 equations for our 4 unknowns. Since not all of us have a calculator capable of solving a 4-equation, 4 unknown system, we could simply substitute in the relationship that Ix is equal to Ia minus Ib here, and that would allow us to evaluate equations 2, 3, and 4 as a 3-equation, 3 unknown system. So let's go ahead and write step number 5, which is just to solve our system of equations. And am I going to use a virtual TI calculator or a virtual Casio today? TI, okay. Continue with the trial. I want to see medium emulator and clear that. And can I get rid of that thing? That'll be an easy way to do it. Okay. Stop. There we go. Okay, so let me clear all this jibber jabber out. So we're working on a 3-equation, 3 unknown system here. So I'm going to go second, and then the tangent button to bring up my system solver. Option 2 is for 3-equation, 3 unknown systems. So in my first equation, my coefficient for IA is 10 plus 6. My coefficient for IB is negative 6. My coefficient for IC is 0. And my constant term is positive 18 when I move it to the right-hand side of the equal sign. In my second equation, my coefficient for IA is going to be negative 6 from the first term, plus 4 from the second term, and that's it. My coefficient for IB will be positive 6 from the first term, minus 4 from the second term, and positive 15 from the third term. And then my coefficient for IC is just negative 15. And my constant term is 0. In my third equation, my coefficient for IA is 0. My coefficient for IB is negative 15. And my coefficient for IC is positive 15 plus 8. And then lastly, actually, so I made an error here because I was putting the stuff in the column for IA and then IB instead of IB and IC. So let me fix that. So that just should be 0. That one was negative 15. And this one is positive 23. Glad I caught that, or we would have gotten some wonky answers. My constant term is going to be positive 5 when I move it to the other side of the equal sign. And solving this system, I get IA is 0.718 amps. IB is 507 over 779, or 0.651 amps. And IC is 0.642 amps. So now that I know these three mesh currents, or actually before we move on from this, anybody that was following along with that calculator, did they get similar numbers? So let's start there. So let's solve it again and just check real quick. So 10 plus 6 is 16. Yeah, I must have just been spacing out here. So the coefficient for IB in the first equation should definitely be -6. So thank you for that, because that is wrong what I have there. Let's just double check the other things. IC is 0.18. That seems legit. Everything else seem okay? Okay. So let's resolve this system. Thank you for catching that mistake. All right, so that gives us 1.445. And 0.852. And lastly, 0.773. Thank you again for catching that mistake. Okay, so assuming these answers are correct, now that we know all of our mesh currents, we could determine any other current or voltage or power in our system, right? So IX, for example, would just be IA minus IB. If we wanted, let's say, the power supplied by my dependent source, we know that the voltage drop across my dependent source is 4. Let's be good with the units here. So this is going to be volts per amp times IX, which is going to be IA minus IB. What's the current flowing into the negative polarity terminal of the dependent source? Well, yeah, so IB flows into the positive polarity terminal, so negative IB flows into the negative polarity terminal. So we could just put a negative IB right here. So I'm just throwing this in my calculator. Let me clear out of this thing. So that would be 4 times what's currently stored in this calculator is X minus Y times negative Y. This is one of the reasons I really like the TI calculators, is it automatically stores everything from a system solver in the memory. And so we would see that our dependent source is supplying negative 2 point something, 0.19 watts of power, which means it's actually absorbing. Ella, how may I help you? So as IB flows around its clockwise path, it is flowing from left to right through the dependent source. Because we are calculating supplied power, I'm looking for the current that's flowing into the negative polarity terminal, which is negative IB. If we wanted the power supplied by the 5-volt source, what would that be? The voltage is very obviously just 5 volts. What's the current flowing into the negative polarity terminal? Just IC. So it would be 5 times IC. So 5 times what's stored in here is Z, gives me 3.866. watts. So those are effectively the basics of mesh analysis when we don't have any current sources to deal with, okay? So very similar process to what we saw with nodal analysis. We got a little bit of setup. I like to put the controlling variable bit at the beginning because that's the easiest or one of the easiest relationships to forget about. And then instead of applying current law, we apply Kirchhoff's voltage law instead. Connor, how may I help you? It's just, yeah. So that's a very good question. So we have now learned two extraordinarily similar circuit analysis techniques, right? Nodal analysis and mesh analysis. Both involve setting up a system of equations to solve for unknown quantities, which can then be used to solve for practically anything else. So Connor's question is effectively, what would be some reasons why I would use nodal analysis over mesh analysis or vice versa? I would argue that whichever method gives you the smaller system of equations is the one that you should probably use. So if you had a circuit with, 8 nodes, but only 3 meshes, do mesh analysis because that's going to be way easier to do. If the number of equations in your system are equal, then I would default to, well, if I'm trying to find a voltage, I would use nodal analysis. And if I'm trying to find a current, I would use mesh analysis. But realistically, you can use them relatively interchangeably. I say relatively interchangeably because technically speaking, mesh analysis can only be used for what are called planar circuits, meaning that you have to be able to flatten out your circuit without having a wire jump over anything in order to use mesh analysis. We will never encounter a circuit that isn't a planar circuit in this class because I can only draw flat things or whatever. But if we had a cube of resistors or something like that, we couldn't actually apply mesh analysis to that. We could only apply nodal and come out with the correct answer. We won't do that, but technically that is a caveat of mesh analysis. All right, so are you guys ready to mess everything up by adding in current sources? All right. So I'm trying to decide how thoroughly I want to mess things up. Like if I want to mess it up so hard that I need MathCAD or not. Let's not do that because the process for MathCAD for a mesh analysis circuit is very, very similar to what we did on Friday. So there's no real reason to do that. Okay. So let's say that I have the following circuit. Let's make this 3Vx, direction down. This will be a 10 ohm resistor. Here we will have a 5 ohm resistor. Here's a 15 ohm resistor. This will be a 4 amp current source direction up. And this will be a 20 ohm resistor over here. And let's define our voltage Vx to be, let's be a dick about it. This voltage. I'm going to move this 5 ohms to the left just for clarity's sake. So I've defined my voltage Vx to be the difference in electrical potential effectively between the top right-hand node and the bottom node. For what it's worth, I love throwing weird stuff like that at you on your tests, where it looks rather difficult, and then when we think about it, we're going to be frustrated at how easy it is, because Like I said, I'm a dick. All right, so we have a circuit now that contains a couple of current sources, okay? So let's do our setup and all of that kind of stuff per usual, and then work it just like we worked the previous examples until we run into a problem, and then talk about how to fix that problem. Okay. So our first step is still going to be to identify our meshes. And our second step is still going to be to assign our mesh currents. And I'm going to just knock these out simultaneously, right? So this could be my mesh current IA. This could be my mesh current IB. And this could be my mesh current IC, like so. So once again, just assigning them all clockwise because that's what I'm used to doing. We do have a controlling variable. So now we'll have to figure out how to express our controlling variable in terms of our mesh currents. And I can identify two different ways to do that for this particular problem that will wind up giving us the exact same result. One is obvious and difficult, and the other one is less obvious and easy. So I'm just going to throw it out to you guys as to how you might suggest doing this. Anybody have any thoughts whatsoever? All right, so it seems like everybody is stumped on both ways. So I'll talk about the obvious but difficult way first. Okay. So I believe that, let me use a different color here, this gray. Our voltage Vx could be expressed as the voltage drop across this 15 ohm resistor plus the voltage drop across this 5 ohm resistor, according to Kirchhoff's voltage law. Effectively, we would be doing KVL around this triangular path to come up with that relationship, right? So we could say that Vx would be equal to, so what would the voltage drop across the 15 ohm resistor with positive polarity on the right be? So 15 ohms, what's the current flowing into that positive polarity terminal? Negative IB. So I'm going to call this negative 15 ohms times IB. And what is the current flowing, excuse me, what is the voltage drop across the 5 ohm resistor with positive polarity on top? So the 5 ohm resistor is shared between meshes A and B, right? So it's definitely going to have two mesh currents associated with it. So we're going to have 5 ohms. Which mesh current is flowing into the positive polarity terminal? IA. So we'll have IA. Which mesh current is flowing into the negative polarity terminal? So we'll do minus IB. So that is one way to express Vx. Connor, have you figured out the other way? Okay. That's all right. So you guys are going to be pissed. It's going to be glorious. The positive polarity terminal of Vx is at this node up here. The negative polarity terminal of Vx is at this node down here, which means Vx is nothing more than the voltage drop across the 20 ohm resistor on the right-hand side of the circuit. Voltage is just the potential difference between 2 points in a circuit. So if I'm looking for the voltage between the purple node and that light orange node, why wouldn't it be the voltage drop across the 20 ohm resistor, which is between the purple node and that light orange node? How could it literally be anything else? So a less obvious but easier relationship would literally just be 20 ohms times IC. Literally, either one of these will work in our system of equations, giving us the exact same information. But like I said, one is obvious and difficult. The other one is less obvious and is an easier relationship. So like I said, I'm a jerk and I like to throw curveballs at you guys to make you think about stuff. All right, so there is our controlling variable relationship. Our next step should be to write our Kirchhoff's voltage law equations, or at least if we were following along with our previous things. Now, as we're going to see here, we're going to run into a difficulty with that. So I'm going to put a blank for step 4 right now. So this is going to be one of the ways that we adapt effectively. And I'm going to put a blank for step 5 right now. And then we're going to jump down here to step number 6. All right, so this is going to seem a little bit odd, but I am going to skip trying to write a KVL equation for mesh A. Instead, I'm going to try to write a KVL equation for mesh B first, okay? So let's call step 6, write a KVL equation for all remaining meshes. And then just to be super clear, just like on Friday, the equations that I'm about to write, we're going to wind up erasing because they're going to be broken. Okay, so just cool your jets for a minute. Okay, so KVL around mesh B. So if we tried to write a KVL equation around mesh B, things would start off pretty okay, right? So we could have 5 ohms times IB minus IA. And then we would have plus 15 ohms times IB. And then we would have to try to write the voltage drop across a current source in terms of our mesh currents, which is literally impossible, right? Because we know that that current source pushes some fixed amount of current around that or through that branch, regardless of what is connected to it. So there's no way that we can tie that current source to the voltage drop across it using our mesh currents, okay? So the best thing that I could say would be voltage drop, so plus V 4 amps, and then I'm going to put top to bottom, so TB, right, is equal to 0. And when I try to write my KVL equation around mesh C, I'll run into a similar issue right from the jump, right? The first thing in my path is that 4 amp current source. So best case, I could write the voltage drop across the 4 amp source from bottom to top plus the 20 ohm resistor times IC is equal to 0, okay? So these two equations have introduced two unknown quantities that are related to each other. They are equal and opposite. So I'm going to do something very similar to what I did on Friday, and I'm just going to add these two equations together because once again, 0 plus 0 still equals 0, right? So if I add these guys together, what I'm going to wind up getting is 5 ohms times IB minus IA plus 15 ohms IB plus that V4A from top to bottom plus that V4A from bottom to top plus 20 ohms IC and set it equal to 0, where these two voltages are going to cancel each other out because they represent the exact same voltage but of opposite polarities. Okay. So what we have effectively done is we have written a KVL equation around this path. Right? So we're starting from the bottom left-hand corner of mesh B, skipping past the branch that contains the 4 amp current source, and then going around and coming back. So this is what we're going to call a super mesh. And this will be super mesh BC, okay? So we have an interior current source, and we are purposefully avoiding it by forming a super mesh around that current source. So the rules for creating a super mesh are pretty straightforward. If we have a current source shared between meshes B and C, like we have here, then our super mesh should just contain those two meshes. So it should just be the smallest number of meshes that bypasses the current source that's messing up our math, okay? So our step number 5 is now going to be write a KVL equation around any super meshes. And I'm just going to take this equation. So KVL at super mesh BC would be 5 ohms times IB minus IA plus 15 ohms IB plus 20 ohms IC is equal to 0. Okay. And I'm going to just erase all of this stuff down here because it's no longer useful. We have all of that information contained in our super mesh KVL equation. So before I move on from that point, are we all understanding why the super mesh is needed here, right? We cannot express the voltage drop across that 4 amp current source in terms of our mesh current. So we needed to come up with a way to avoid it when we write our KVL equation. We did that by creating a super mesh, which is just the smallest combination of meshes that avoids us taking the voltage drop across that particular current source, which in this case would just be mesh B and mesh C. Now, our expectation is that each mesh should give us one relationship. Well, we have a KVL equation that is around two meshes, so we need to figure out what the other relationship is. So step number 4 is going to be write a current relationship equation for each current source. So let's start with the 4-amp current source because that's the one that we've been looking at. Okay. So which mesh current is in the same direction as the 4-amp current source as it flows around its clockwise path? IC. So it's going to get a plus sign. And which mesh current is in the opposite direction? IB. So it's going to get a minus sign. So there's our first current relationship equation. We also have that dependent source on the left-hand side. So we're going to have a second relationship here, 3Vx, and that's going to be equal to what? Negative IA. All right, so let's jump back down to step number 6. Write a KVL equation for all remaining meshes. So how many remaining meshes do we have here? So can we write a KVL equation for IA? No, it contains a current source. So let's look at something really quickly, right? So here's our one equation for Vx. Here's a second equation, a third equation, and a fourth equation. How many unknowns do we have? 4, IA, IB, IC, and Vx. So we already have enough equations. So we've accidentally just gleaned something important here, right? Whenever we have a current source on the perimeter of the circuit or on the outside edge, we are only going to have a current relationship equation. We don't need a KVL equation for that mesh at all because we effectively know what that mesh current is. The current source is telling us, right? So in this particular problem, we don't have to do literally anything for step 6 because there are no remaining meshes for us to write equations for. So I could adapt this very slightly and say, write a KVL equation for all remaining meshes which do not contain current sources. To be more clear. And then lastly, here at step number 7, we would simply solve our system of equations. So since we have a well-defined system and all of that kind of stuff, and I've solved systems on multiple different types of calculators at this point, I'm going to leave that as an exercise to you guys. There's one last thing that I want to show you all, okay? So are we okay for me to move on to a third and final example problem? All right. So what should step 1 be? Identify our meshes. So here's a mesh, and I'm going to call it IA. So we'll knock out step 2 at the same time. Here's a mesh, which I'm going to call IB. So we've got steps 1 and 2 taken care of. What's step 3? Do we have any controlling variables? No, there are no dependent sources, so we can move on to the next step. What's our next step? Current relationship equations. All right, so let's start with the 10 amp current source. What's our current relationship equation there? So 10 amps is just equal to IA. And then we have the 3 amp current source. What's our current relationship equation there? 3 amps is equal to IA minus IB. What should our next step be? So write a KVL equation around any super meshes that we have. So there is arguably here a super mesh, right? So if I define this as my super mesh AB, it encloses the 3 amp interior current source, exactly like it's supposed to do. Connor, you were shaking your head incredulously. Why were you shaking your head? Yeah, we can't write a KVL equation around this path because this super mesh contains a perimeter current source, right? So because this super mesh happens to contain a current source on the edge of the circuit, we can't write a KVL equation around it. So a better question would be, do we need one? And the short answer is no. We have 2 equations for a 2 unknown system. We are done. Why continue working the problem if we have enough information to just solve the damn thing, right? So yeah, so let's see. So IB would have to be 7 amps. Yeah, sure. And then we're good. Okay. So all I was trying to show you guys with this particular example, because I know for a fact it's going to show up in your in-class assignment problem 3, and also it'll show up in your homework a couple of times, is that when we enclose an interior current source, like we did with this green super mesh path, if that path happens to contain a perimeter current source as well, we will only have current relationships for that super mesh equation, or for that super mesh, right? There is no way for us to write KVL around that path because it contains a current source on the perimeter of the circuit. All right, I'm done ranting at you guys for today. So work on your in-class assignment. If you have any questions about anything, please feel free to ask.